Hello, everyone. Welcome to this lecture of computer system security. We are going to continue our discussion about the encryption modes. If you remember, we've talked about the encryption mode. We said that we have an encryption algorithm. It might be DES, triple DES, or AES, or whatever. And now we want to encrypt the data, which is I'm just reviewing the kind of problem statement of encryption mode, what the encryption mode is. So we have an encryption algorithm. It might be any algorithm, and we just wanna now use that encryption algorithm and encrypt the data, which is in terms of size, it's bigger than the block size or the uh, mm, data size of that encryption algorithm. For example, we have, if we are talking about DES, the block size is 64 bits of data, and our data might be, for example, let's say 1 kilobytes of data, which if I convert it into bits, it's going to be way more than 64. So the encryption mode is a technique that it's not talking about how to encrypt, but it tells us how to put a series of encryption after each other or next to each other so that we can encrypt a bigger block of data using a given encryption algorithm, a given block cipher. So we use encryption modes in order to somehow expand the size of the block ciphers that we have. Because when the researchers or people, they sit and develop new encryption algorithm, it might be anything that they like. It might be 64, 128 for AES or whatever. But when it comes to the actual use cases or the actual application, the size of the data that we want to encrypt it, it might be anything. It is very, there is a very low chance that, for example, you get your data and the data is, for example, exactly 64 bits. So in many cases, the data is less or more, most of the time is way more than the block size of this cipher. So we have to use encryption mode. We talked about two of them. One of them is electronic code book, which is a kind of simplest one. In the electronic code book, we just break our data into portions, or we slice it into slots that each portion has the same size with the block size of the cipher or the block cipher. For example, if we are using here DES, which takes 64 bits of data, whatever the size of my data is, I'm gonna break it into into blocks of 64. So the first 64, second 64 bits, third 64 bits, and I'll go all the way until the last block of 64. And of course, I use some DES that work in parallel, and all of them, they work with the same key, because of course we don't have multiple keys. All this data belong to one same file or one same message, so we are not going to use different keys. We only have one key. And we talked about it. This is a ECB or electronic code book. We said that it's very kind of, in terms of security, it's very weak, because if the attacker somehow breaks the key, he or she will be able to kind of steal all the information. The next one, and here also another weakness that we see, that there are some correlation between the input data, not blocks of data, the input data as a whole, and the blocks of the encrypted data. So this is a plain text as a whole, and this is a ciphertext as a whole. Although we have broken this into blocks of 64, 64, and so on, but since there is no relation between the consecutive blocks, the correlation is kept the same, and we can see what this original image was. The next one we introduced was cipher block chaining, which is slightly better. And here we break again the data into multiple blocks of 64 or whatever. And any cipher block I will be used as somehow as the input of the next block. So in the first block, we get the first 64 bits of data. We encrypt it using the key and using the DES or whatever other encryption algorithms we get. and we get the ciphertext. Ciphertext 1, which kind of is corresponding to the plain text block 1. So we use this ciphertext and we XOR it with the plain text of the next round or next block of data. So this is the second block. We don't feed the second block as is. Before feeding it into the encryption algorithm, we first XOR it with the ciphertext of the previous round of, previous block number 1, and then we XOR it to encryption. And of course, here we are making some relation between the first block and second block. So in order to, for decryption, in order to be able to decrypt the second block, I need to have the first ciphertext or ciphertext of the first block. And this way that kind of function or that chaining will happen. And if you put the data together, you don't see such kind of such images like this, that you can easily say that what's the encrypted and what's the relation between the encryption or encrypted data as a whole and the plain data as a whole. Okay, these two, we talked about them. Now I'm going to talk about 3 more encryption modes, which are this is what we are going to do this session. We will be talking about cipher feedback mode, output feedback mode, and counter mode, which are all kind of valid and relevant, and they're being used in many commercial applications. Okay, but before getting into them, before talking about the details, I want to talk about another feature that these 3, not the 2 previous, these 3 offer. And that feature is that these 3, CFP, OFP, and CRT, they also let us to change or to convert a cipher, a block cipher into a stream cipher. What does this mean? If you remember, we've talked about the block cipher versus a stream cipher. We said that in block cipher, you have to input a block of data. That block of data has a fixed size, for example, in DS64, in AES-128, and you encrypt it using your encryption algorithm, and you get the same size of data at the output. So everything, every time you want to invoke this encryption algorithm, you need to you need to input to that 64 bits of data. There is no way to increase or decrease it. If your data is bigger, you need to break it into multiple blocks. If your data is less, you need to append some data to make it 64. So this is called block cipher. In contrast, we talked about also cipher mode. Stream mode or stream cipher. And I said that in a stream cipher, our data comes in a stream. For example, the first byte comes, then next byte, and we encrypt the first byte, and then the second byte, this is byte 1, and then byte 2 comes, we encrypt it, and then byte 3 comes, we encrypt it, and so on. This is a stream. Okay, these 3 encryption modes, cipher feedback, output feedback, and counter mode, they give us this option, this capability to convert block ciphers like DES, like TripleDES, and AES that we've talked about them. They give us this option to convert these block ciphers into stream ciphers, meaning that using these 3 encryption mode, we will be able to encrypt and decrypt data which are less than 64. For example, you might be able to use 10 bits of data using DES, which is normally, it's not possible, it's not feasible, because DES needs 64 bits to start the encryption. But if you use the DES in the CFP mode, you would be able to encrypt only 10 bits of data. Okay, so this is a great opportunity, great feature that these 3 modes of encryption give us. So now let's get started and talk about the details of each. The first one is called cipher feedback or CFP mode. And this kind of architecture shows how the cipher feedback works. And of course, you know that we still have some blocks of data. Here are our blocks of data. Plain text number 1, plain text number 2, plain text number n. But here, they have the size of S bits. The size of plain text or each block of plain text is S bit. S can be, for example, in DS equal to 64, can be set to 64, but it might be any other size. The S might be also 10, S might be 15. The way it works is this. And of course, we have the same key for all blocks. So the key for all blocks, as you see, is identical. We don't have many keys. There is only one key. This has many reasons. First of all of these blocks P1, P2, up to Pn, they belong to the same message or same file. So we don't want to encrypt them using different keys. This is the first thing. Second thing, key is something valuable. Generating key is difficult, is time consuming, is energy consuming. And on the other hand, storing the key and attaining the security of key is also needs some effort. So that's why we don't want to increase the number of keys to too many. We just try to go with the minimum number of keys required. So all of them, again, all of them work with the same key. And here for the first block, as you see, we have an initialization vector. We talked about this initialization vector. I said that in some algorithms, we apply some initialization vector. In some of the modes, including the CFP mode, we apply the initialization vector so that if one single plain text or plain block of data is applied for encryption multiple times, every time we get something different. So because the initialization vector, it normally comes from a random number generator. That's why every time, even if you apply the same input plain text, since the initialization vector is different, you'll get, since the initialization vector is different, you'll get different ciphertext. That way, we can claim that even if the plain text is equal, the ciphertext we get are going to be different, which is a strong point. From the security standpoint, we like it to happen. Anyway, we have the initialization vector in the first round or for the first block. It comes and it's getting encrypted. We encrypt it, and the output of encryption gives us something. Let's call it O, output O1. This output O1, of course, it has, let's assume that we are talking about DES. What I'm saying is applicable for all, and is true for other encryptions, other block ciphers, like triple DES, AES, or whatever. But just we need to agree on one. Let's suppose that we are talking about the DES, which has the block size of 64 bits. So this means that this encryption is going to be done based on DES. So since this is DES, the size of initialization vector should be 64 bits. And the output we get here, output of the encryption, is going to be again 64 bits. And our key is also 64 bits. That you remember, out of that, 8 bits of that is going to be the parity. So the actual key is for the 56 bits, but anyway, we assume that the key is also 64. So I'm talking about the O here, the output O, which is the O1, which is the encryption text or the cipher text coming out at the first block. And if you remember, in the chain mode, we used to get this and XOR it with a plain text, which is also 64 bits. But this is not the case here. Let me clear some of these Okay. Okay, give me a second. Okay, yeah. So this is 64, since this is DS. This is 64, again, since this is DS. And our plain text is not mandatory, is not required to be 64. It can be anything. So I mentioned here S. Let's assume that S is 10 bits. So what we do in this cipher feedback, we get the 10 upper bits of the output of the encryption. We XOR it with the plain text, and this is gonna be our cipher text of first block. So we call it C1, ciphertext of the first block, which every block per our assumption is going to be 10 bits, not more. It might be anything up to 64. Of course, it cannot be bigger than the block capacity, the block cipher that we have. It cannot be bigger than 64, but it can be anything from 1 to 64. So we get this 10 bit, and this is going to be our ciphertext of the first block. Okay, we get this first cipher block, 10 bit, and we feed it to the next block. And it's going to be used in the next block. How this initial, here we use the initialization vector that normally gets a random value. Whatever value we have in the initialization vector, we shift it to left S bits, we shift it to left S bits, and put this C1 at the right side of that. So C1 goes here. So whatever the, I have some more examples for this to make it more clear, but the initialization vector, whatever the initialization vector is, we shift it to left S bits, and we append this C1 from the right side. And this way, second block's input is going to be a mix of, is going to be a concatenation of the initialization vector and C1. And we apply it to the second DES, which is again here, assume this is DES with the 64 bits. And it gives me another output, which is again 64. And I'm going to do the same thing again. The upper 10 bits are going to be used and exported with the second plain text or second block of plain text. And what I get at the output, I call it second block of cipher or C2, and then I continue the same thing. So this way, you see that we are, first of all, every block I is kind of related to previous block or previous blocks. This is the first thing. Second, the block size can be anything below or equal the block cipher size. So if you are using DES, which gives you the block size of 64, your actual block size can be anything between 1 to 64. Okay. Now I'm gonna show you more how that feedback works, because you may say, okay, where's the feedback? Where the feedback name comes from? Okay, the feedback comes from here. This diagram here shows, this architecture here shows what the, why do we call it a feedback, cipher feedback? Here, again, let's assume that this is block number 1. Initialization vector comes, it applies, and then we get something B bits. B here is the size of the block, which is 64 if we assume DES. We encrypt it, it gives us again another B bit, 64 for DES. And here, we only use some bits, let's say 10 bits of that, or S bits of that, and we XOR, and that thing, whatever we get, is gonna be feedback to the initialization vector. So that's why we call it feedback, because this is C, for example, 1, if we are talking about block 1, this is C1, which is gonna be feedback to the initialization vector. Or we can see it like, we can draw it differently. This is one way that we can think about it. Or that conceptually is correct, or we can talk about it this way. This C1 is going to be fed to the second initialization vector, or is going to be fed to the is going to be used as a part of, not whole, as a part of the initialization vector for the second block. We can this is a actual way that we implement it, but conceptually we can say that this CI is going to be feedback and makes the initialization vector for block I plus 1. That's why people call it feedback, because here there is a loop between the CI and initialization vector. Of course, this is the cipher of the block number I, and this is the initialization vector of block I plus 1. Okay, so I guess I talked about almost everything, and here are the kind of math equation that shows how it works. Here we say that I1 initialization 1 or input 1, if we call this I at this point, I1 equals initialization vector, ij for other blocks, it comes from this equation, which is something kind of just math equation of what I said. Logical shift left, we are shifting toward left. Oh, sorry, we are taking a LSB, the least significant bits from the right side. This, let me show you this animation first, and then I go to this. Yeah, look at this. This is what. Let me clear the writing, and then okay. This is what's going to happen. We have a B bits or 64. If we are talking about DS, that's going to be encrypted. It's going to be encrypted, and we get something at the output of the encryption. Out of that, a portion of that, which is S bits, is going to be used and is going to be XORed with the plain text in block number J, and it produces ciphertext of block J or CJ. Of course, the color should be different. Don't the color shouldn't confuse you. Here we had yellow, and when it comes here, the data is going to be changed. But I just kept it in terms of size. And then this is going to happen. We fit this back for the next round. This is going to be the input for the next round. A portion or least significant portion of the previous input, the least B minus S bits of the previous input, which is being concatenated. This is a concatenation operator. It means that it puts the string and just put them together, which is concatenated with the cipher of previous block. So that's why we say there is a feedback here from block J minus 1 to block J. And this is the equation for output. Output is this point. For all of the blocks, output J equals encryption of the input of that block and the key. And key is equal for all of them. And then cipher of each block is plain text of that block, which is being XORed with the most significant bits of the output, this point, S bits. So we take only S bit of the output, not all of that, and we XOR it with the plain text, and what we get is a ciphertext. Okay, let me go back here. I'm going to also give you a numerical example for making it clear. We have two more. I'm not, of course, I'm not giving example for all of them, but let at least give an example for one of them so that you can understand it easier. Assume that the I'm assuming just some bits. Let's assume that we are talking about an encryption which has a block size of 16 bits. And let's assume that here we have 1, 2, 3. I'm writing number in hex. and let's suppose that key is something, doesn't matter, for example, AB01 in hex. And once we encrypt it, we get something. Let's say A02, for example, B in hex, we get this. Out of these three, we discard this portion. This portion we don't keep it because the size of our data is only 4 bits. Here we are assuming 4 bit in my example. And whatever, let's assume that the data is, for example, 1. And now these two are gonna be XOR. This is A. I'm gonna do the XOR. I'm gonna open up the XOR, and this is 1. If we XOR them, we'll get B. So here we get B. B is our ciphertext. So C1 becomes B in hex, and then C1 comes here. We had 1, 2, 3. Out of the 1, 2, 3, 2, 3, 4 stays, and B will be appended in the right. So this is going to be the next input to the encryption. And the key, our key is the same, AB01. Let's assume we get something. For example, it gives us 087C as the output. Again, the 12 bits, we just discard them. We don't want them. The 0 is going to be, and let's assume that the plain text number 2 is, for example, let's say 9. 9 and 0 are going to be XOR. We get 9. And 9 is going to be applied to the input of the next level. So what I get for the next level is going to be B 4, 3, and 9. This is the input of the next round of next block of the algorithm, and so on. I think that this example makes it more clear for you. But please keep in mind that when I applied something here and I assumed something, I didn't follow the encryption. I just came up with some random number. So this number is not the encrypted of the input. I just came up with something, but I wanted to show you that how that shift happens, how the feedback from block number I to block number I plus 1 happens. We use the S bits of this cipher or the output of the encryption, and after XORing it with the plain text here, we use that S bits and we feed it from the right side, we shift it from the right side to the input of the previous stage or previous block and use it as the input for the next block. I think this should make it clear. Now let's talk about the decryption part. Okay, we saw this animation also, so let's go forward. Okay, here is the decryption process. In the decryption process, we kind of use the initialization vector. Whatever the initialization vector used, we need that. The initialization vector, we should have it at the receiver side, or when we want to decrypt the data, we need to have the exact same initialization vector. Interesting point. Unlike the other method that we just talked about, unlike the chain mode, cipher block chain mode that we just talked about it, here for decryption, look at this is a very important point, guys. For the decryption, we are using another round of encryption. So we don't need to do the encryption, the decryption process. We do encryption. The way it works is this: we take the initialization vector, we encrypt it, we get the output. Again, we only use the upper S bits, and we XOR that with the ciphertext, block ciphertext 1 or ciphertext of block 1, and what we get is the plain text. And the reason, you may wonder how, the reason somehow relates to this XOR operation. Let me give you an example. Suppose that I have this data 1011, which is B in hex, and I XOR it with, let's say this number, with 7, for example, with 7. If I XOR B with 7, what I get is 0, 0, 1, 1, which is C. Okay, if I XOR it another time with the same thing with 7, let's do it. We get 1, 1, 0, 1, which is B. So XOR has this property. If you do one XOR operation, if you repeat an XOR operation with the same, of course, value, I'm here XORing with 7, and here I'm repeating that XOR. They cancel out each other. Even number of XORs, even number, for example, if you do XOR 2 times or 4 times or 6 times or any other even number, it is identical. You are not in fact changing your data. So that's why here we encrypt, we get that key, we again generate that, and we XOR the ciphertext with that key. So this key, this output that comes is the exact thing that we generated in the encryption phase. So we XOR it for the second time in the ciphertext. So remember what was, let me write the equation. What I'm writing it here. What was our ciphertext? We said that ciphertext 1 is plain text 1 XOR, let's call this output upper S bit. I call it OS. Output OS. What I'm doing here, I'm XORing the ciphertext, which is this, another time with OS. So these two XORs cancel each other, and what I'm getting at the output is the plain text. So XORing 2 times or 4 times or 6 times or any other even number, it means that you're canceling that XOR operation. That's why in the cipher block mode, we don't need to decrypt. We just encrypt again the initialization vector. What we get, we only use the upper S bits of that, XOR that thing with the ciphertext, and it gives me the plain text. For the next round, again, I do the same thing. I take the ciphertext and I generate the input the same way I explained. For example, if here is 1, 2, 3, 4, and here, for example, is B, the next input is gonna be 2, 3, 4, B. 2, 3, 4 is gonna be encrypted using the same key. It gives me something. Only S upper bits is going to be used. I XOR it with the ciphertext, and what I get is gonna be plain text. Next round and next round, and so on and so on. And here is the kind of the feedback that I just talked. What you get from the ciphertext is gonna be applied to the right side of the input of the next block. And here are the kind of math representation, which again is kind of saying the same thing. So this is called cipher feedback mode. And the interesting point about it, we don't need to do any decryption for this mode of encryption. If you use the encryption, any encryption mode, it applies to DES, triple S, AES, even asymmetric ones. If you apply it, if you use them in the CFE mode, you don't need to do any decryption. Okay, now let's talk more about the CFE mode. What are the kind of options that we have? The first option that here we have and is very important, is the size of S. S, which is the size of plain text, can be chosen as anything smaller than B. So if your B or block size is, for example, 64, your S can be 10. Your S can be picked as, your S can be selected as 10. And this means that you can change or convert the block cipher DES into a stream cipher. Now you can use DES and you can start encrypting 10 bits, 10 bits, 10 bits of data. The first 10 bits, the first block of 10 bits, the second block of 10 bits, the third block of 10 bits, and so on. So this means that we have converted the block cipher into a stream cipher, which is very important. So this is the first feature or option that we get. Okay, it uses the initialization vector. Initialization vector is something that we use it in order to guarantee that if the same input text or plain text is fed into the encryption, we get every time we get different ciphertext. Otherwise, if you apply the same plain text, you'll be getting the same ciphertext, which is not good. And the initialization vector can be sent as a clear. We don't have to kind of protect its security. The only thing that we should make sure about the initialization vector is its integrity. It means that the initialization vector should be kept unchanged. We don't have to keep it secret. I can, if I have encrypted something, I can give you my initialization vector. That's okay. But I should make sure that when I'm using my initialization vector in the decryption process, that's the exact same initialization vector. Because if you change the initial, if the attacker comes and changes the initialization vector, what I get is going to be different. The plain text, at least for that block, is going to be different. We'll be talking about it, that what would happen if some bits of the initialization vector or ciphertext are not okay. Okay, in terms of dependency, because one of the basic goal is to make some type of dependency or relations between the block number I and previous blocks. In this mode of encryption, block number J depends on the plain ciphertext J, or the output of the encryption at block J depends on the plain text J, which is of course true, and also all prior or preceding plain text blocks. So CJ depends, is somehow a function of PJ minus 1, and so on all the way up to P1. Okay, and the last thing is about that we need to know about this is the kind of the error propagation. Proper decryption of a correct ciphertext block needs preceding B over S bits of the ciphertext to be correct. If they are not correct, that error will happen. That I'm gonna talk about it here. You remember we talked about the error propagation. If we said what happened if some bits of the ciphertext goes wrong. Okay, let's talk about it. For example, let's say S is 10. We have 10 bits, and one of these 10 bits, assume these are 10 bits, one of them is going wrong. One of them, for example, instead of 0, it used to be 0, but someone has changed it and now it is 1. That is a specific bit. What would happen? Of course, when we are doing the decryption process, this is a decryption process. The plain text for that block is going to be garbage. Is going to the plain text, sorry, for that block is going to have an error in the exact same bit position. For example, if this, let's say this 10 bits is, let's say 2B3, this is a 10-bit number, assuming that this is 2, since this is smaller than 3, this is 2, and this is B, and this is 3, okay, 10 bits. Let's say this bit goes wrong and this one becomes 0. So instead of 0, 1, blah, blah, I'll get 0, 0, B3. This is 1 bit error. When I do this XOR operation, the plain text will have error in the exact same bit position. The plain text of that block. We are talking about block number 1. The plain text in the decryption process, the plain text of that block will observe a bit error in the exact same position. So this is for block number 1. But what would happen to the next block? This error in the ciphertext, because error happened here, this error will propagate to the input of the next block, and through here goes to the input of the next block, and all the way it lasts for B over S different blocks. And you know, this is the encryption. If 1 bit here is changed, the output is going to be totally different. So this plain text number 2 is going to be totally garbage for the next block, that still we have the effect of this error bit, the plain text is going to be totally garbage, and so on. So we say for the next B over S, so if B is 64 and S is 10, it lasts for 6 blocks. The first block experience only 1 bit error. Second block is gonna be totally garbage. Third block and all the way up to the 7th block are gonna be totally garbage. So we lose 1 bit in the block that the error happened in the ciphertext of that block. We lose 1 bit there, and then we lose the whole B over S blocks of kind of blocks which are after this block. So this is the error propagation analysis for this encryption mode. Okay, I think we've discussed about it enough. Let's go to the next encryption mode. The next encryption mode I'm going to talk about is called output feedback mode, which is similar to the cipher feedback, but cipher feedback, we used to use the cipher, which is here, the ciphertext. We use the cipher as somehow and fit to the next block. But here we are using the output. Here, this is the output. This is the output of the encryption. So the output of the encryption is being used and is being fed to the as the input to the next block. Again, the same thing here. You see, we get this output, and it's gonna be feedback. That's why we call it feedback. If, for example, this is 64, let me again give you some number. That might be kind of the easiest. Let's assume that here we start with 1, 2, 3, and key is something. We encrypt it and we get, let's say, 0 to 8A. Out of that, we again, it's up to us. We take some bits of that. We can take, for example, let's say the upper 4 bits or upper 8 bits or whatever. It depends on the size of the block that we have. For simplicity, let's assume that our block is, for example, 1 byte. So we get these 2 hex, we XOR with the plain text, and this is going to be the cipher. In the previous mode, we use the cipher to feed it, but this time we use this. I've used this portion, and we feed it to the next, and the next one is going to be 3, 4, for example, 0, 2, and then rest of the operation. Okay. Another, so the major difference is that we are using the output of the encryption to feed to the as the input of the next block. This is the first big difference. There is another difference that here we are not using initialization vector. Something else is going to be used, which is called nonce. What is a nonce? Nonce is in fact an initialization vector, but it should kind of fulfill a feature, and that feature is that it should be a unique initialization vector. The initialization vector should be unique. Otherwise, the message will be encrypted with the same Q stream. It means that we're going to get the same cipher, because we are not here using the, look here, the output that we are getting at this point is not the function of the plain text. It's only the function of the output. So if the initialization vector is not unique, the key of encryption, sorry, the chain of encryption is going to be always the same. So that's why for every message that we want to, or every file that we want to encrypt, we should use a unique nonce or unique initialization vector. The difference in the previous one, we used to use this portion, which is a function of the output plus the plain text. So the plain text every time changes. So I don't need to make sure, or I don't need the guarantee that the initialization vector is unique. But here for this mode, the initialization vector should be unique, that we call it a nonce. Okay, and here is the decryption process. In the decryption process, again, we get the nonce. Again, we encrypt it. Look at here again. This is a nice feature that again we don't need to do the decryption. Here again we encrypt the nonce. What we get is going to be again export by the ciphertext of block 1, and the output gives us the plain text. We use this output and we kind of generate the input of the next block, block number 2, and the same thing. And here are the kind of math representation of the same thing that I just said. Okay, as I said, the initialization vector should be unique, that we call it a nonce. Otherwise, the same encryption chain will happen to different plain text, which is of course something that we don't need it. Again, the nonce like initialization vector, we just need to keep it, we just need to make sure about the nonce integrity. We don't need to keep it secret. It can be open to everyone, but we should make sure that it's not being changed by anyone. One negative feature is that if due to any reason the nonce is kind of attacked and even one bit of the nonce is changed, the whole cipher is gonna go lost, and we will not be able to decrypt it anymore. Because look at here, the nonce is going to be affecting all ciphers and is needed for decrypting all ciphers. So only if one of the bits of it goes wrong, we of course will be losing the whole block that we had. I'm talking about, for example, the whole file or the whole message. We will not be able to decrypt it anymore. And ciphertext J depends on plain text J only, does not depend on the preceding plain text block. And in terms of error propagation, 1-bit error in the ciphertext has an effect on the decryption of only that ciphertext block. If the ciphertext, again, look at here, if something in ciphertext goes wrong, only we have error in the same bit position of the plain text, only in that block. Because this ciphertext is not going to be fed to the next block, there is no relation between ciphertext of block I and I+1. So the plain text of that block only experience some error, and that's going to be in the exact same bit position that we have error for the ciphertext of that block. So which is this is a good property, of course. This is a good property that we like it. And so I put a plus here. This is a good property, but this is a negative property. We don't, in terms of security, we don't like it. Okay, for the for the attendance code, please use CRT. CRT all uppercase for attendance code of this video. Thank you. And the last encryption mode that I'm going to talk about is called counter mode. In the counter mode, we use different initialization vectors or inputs, let's say, which they come from a counter value. So we have a counting value, we use it as initialization vector, and there is no feedback between the blocks. So block number 2 is not getting anything from block number 1 to generate or to produce its input. The only thing is that we have a counter here, and this is basically the input of the first block, input of the second block. It is somehow related to this. We can say that whatever this counter is, we increase it, we increment it by 1 or by whatever number. For example, counter 2 can be counter 1 plus 1, or counter 1 plus 2, plus some strike. That's why we call it counter mode. The counter value should be increased at each block, and that's it. The rest of that is exactly similar to output output feedback mode, the previous mode that we just talked about. And again, here, this is the encryption. We get the counter 1, we get the key, we encrypt, and the plain text is going to be XORed, and it gives me the ciphertext. And again, the plain text, for example, if the block size is 64, if the block cipher is 64, the plain text doesn't have to be 64. It can be 10 bits. So we only look at the upper 10 bits, and we discard the rest of that. We take it, we XOR it with the plain text, and what we get is the ciphertext of this block, which is again 10 bits. So all of these 3 algorithms or encryption modes, we just talked about them, they have this capability to convert a block cipher into stream cipher. And when we go to the next block, again, we will be using the same block size, 64. The counter is now incremented by 1 or by some number, and then we do encryption, and then the next plain text is again 10 bits. And we go forward that in this kind of architecture, and it can encrypt any size of data for us. And of course, the size of our data, which is S, can be as big as B, or the block size, which means that we can go from 1 all the way to 64. If we are talking about, for example, 64-bit encryption, our plain text size can be maximum 64, but it can be anything less than that as well. And here's the decryption, which is pretty straightforward, similar to output feedback mode. Again, we get the counter, we again encrypt it. Again, there is no need for decryption process. There is no decryption process, although we are doing decryption, but we don't need to do the decryption. Again, we get the counter, we encrypt it, and any number of bits that we need, we just take it and we XOR with the ciphertext. And the reason that we don't need the encryption, I explained it. This is the second time I'm saying, when you XOR the same thing, some number with the same thing twice, that XOR operation will cancel out. So we get the same ciphertext, we XOR it with the same value, and that XOR is just canceling the previous XOR, and we get the plain text. Okay, I think that should be enough for today. We have, okay, just let me talk about, make the final discussion about the counter mode. Blocks can be decrypted independently. This is a good feature. If you look at here, blocks can be decrypted independently. We don't need, for decrypting block 2, we don't need to do block 1 first. Block 1 and 2 can be done in parallel, which is something good. It helps us to increase the speed of decryption process. This is something that we like it. And the XORed, the values to be XORed can be even pre-computed. It means that you can, for example, I know that I'm the receiver side. I want to decrypt, let's say, 20 blocks that you will be sending me. I have not received the ciphertext yet, but I know the counters and I know the key, of course. I start producing output 1, output 2, all the way to output 20. I produce all of them ahead of time. I still have not received the ciphertext. The ciphertext is not delivered to me, but I generate these two output 1, these output 1, 2, up to output 20. And the moment you give me the data, the moment I receive the ciphertext 1 all the way to ciphertext 20, I have output 1 to output 20. I put them and I just do the XOR operation in a super fast amount of them, in just nothing, in 2 cycles of a CPU period. And then I'll get plain text 1 to plain text 20. So this not having any feedback between the mode is very interesting feature that led us to implement the counter mode in a very fast way, especially when it comes to decryption, like I explained it here. So this is again a very big plus that we like it. Yeah, and I talked about this, that here for these three, we only need to do the encryption. We don't need to do the decryption. That's why sometimes we hear more about encryption and less about decryption. And here is another point that output feedback and counter mode, they make a synchronous stream cipher. And cipher feedback, it makes self-synchronization. I think that should be enough for the day. We'll continue next. In next video, we start talking about hash function and message authentication using hash. Thank you for attending today's class, and have a good day.